Okay, a couple of problems from section 1.6. These will go pretty quick. We had some really useful ideas in the notes and in the book about where a function is continuous. So when you look at a function and you're asked to find where it's continuous, what they like is the interval of x values where the graph is one contiguous piece. Okay, so the intervals in which we have no breaks in the graph. Okay, so first of all, number 16, they give us a function 3 minus 2x minus x squared, and they say, state the intervals of x values where the function is continuous. Okay. Well, this is an easy one. This is a polynomial function. One of the theorems we have in this section is that polynomials are continuous for all values of x. Any polynomial you graph, whether you have 1 or 2 or 3 little curves in it, okay, they're always continuous functions from all the way left to all the way right. So we can say that this function is continuous on the interval negative infinity to infinity because it's a polynomial. Okay. Now, number 22 is a rational function. It's going to be a little bit more difficult. But again, we had another theorem about where rational functions are continuous. They're continuous on any open interval where the denominator is not 0. Okay. So, for instance, when we look at this rational function, the denominator, x squared plus x minus 2, we have to look and see, is that ever equal to 0? Okay, when you divide by 0, the function isn't even defined. So it certainly can't be continuous for any value of x which would make the denominator 0. Now otherwise, the function's perfectly okay. So we kind of move over to this question. Where is the denominator equal to 0? Well, this one's not too bad. It's a quadratic equation. We can solve it by factoring. This one factors as x plus 2 times x minus 1. Okay. So it's going to be, the denominator is going to be 0 when x is negative 2 or positive 1. Okay. So what does that mean? Those two x values make our function undefined. So it's continuous on any open interval that doesn't contain these two x values. So actually it's going to be 3 intervals in this case. Okay. These are the two x values that create a problem. So our function is going to be continuous from negative infinity, okay, up until the first one, which is negative 2. That's the one on the left, right? Okay. Then it's going to be continuous again for every x value between these 2 points, so from negative 2 to 1. Okay. And finally, it's going to be continuous everywhere past positive 1, so from 1 to infinity. Okay. So 3 intervals of continuity because there are only 2 problems. And those are the 2 problems when the denominator is equal to 0. Okay. So that's another example. Now I'm going to look at one more here, which needs a little bit more space just to even write the function. But basically the same directions. This is number 28. And they ask where the following function is continuous. F of x equals, and it's a piecewise function, x squared minus 4 when x is less than or equal to 0, and f of x is 3x plus 1 when x is greater than 0. Okay. Now, piecewise functions actually aren't that bad. In this case, both pieces are polynomials. So this piece is going to be continuous everywhere to the left of 0. This piece is going to give us a continuous graph everywhere to the right of 0. The only question is really what happens right at 0. Okay, is this function continuous at 0? Because we know that 2 pieces can not meet up, or they can meet up. Now, if those 2 pieces do meet up and form one contiguous graph, they'll be continuous everywhere. Okay? However, if this piece stops abruptly when x is 0, and the second piece starts abruptly somewhere else, then it has a discontinuity of 0. So it's actually pretty easy to answer that. We're only interested in that one point. Every other value of x other than 0, we know to the left and right the graph is a nice contiguous piece. So we ask what happens to this function when x approaches 0 from the right, and what happens to this function when x approaches 0 from the left. Okay. Well, and again, that's the right way to look at it because we can definitely say what happens to each side separately. You see, from the right side, okay, x is bigger than 0. So our function is 3x plus 1. Okay. Now, there's no problem putting 0 in for x here, okay, because it's well defined. Okay. So 3 times 0 plus 1, let's see, 0 plus 1, which is 1. Okay. So when x is bigger than 0, we use this formula to evaluate our function. We know that the function is going to be approaching 1 as x approaches 0. Okay. Now, on the other side, again, we can use the replacement theorem because our complicated piecewise function is just equal to x squared minus 4 as long as we're sticking to the left side of 0. Okay. So, well, again, replacement theorem, we use that. Now we can just use direct substitution. There's no problem putting 0 in for x. So when we put 0 in for x, we get 0 squared minus 4, which is negative 4. Okay, these two limits don't agree. What that means is that as x gets close to 0 from the left and from the right, these two pieces of the graph are going to approach different y values. So it's not going to be continuous at 0. Okay. So the answer to the question here, I'll have to erase some of my work, is that f of x is continuous on two separate intervals, everywhere to the left of 0 and everywhere to the right of 0. Okay, it's not continuous at 0 because the function is approaching two different numbers, one from the left of 0 and another one from the right of 0. Okay, so that's those are the biggest intervals of continuity we can have for this function.